Welcome to today's Explainer. I am so thrilled to have you here. Today, we're going to unpack this massive, largely invisible infrastructure that literally every single one of us relies on every day just to find our way around the world. And to do that, we're going to lean heavily into fundamental L4 position fixing principles. If you're not familiar, L4 refers to those advanced data processing frameworks and multi-frequency tracking systems that allow for hyper-precise, localized tracking right here on Earth.
It's one of those things we completely take for granted now, right? I mean, how does that tiny blue dot on your smartphone screen know exactly where you are on a planet of 197 million square miles? It honestly feels like magic. But as we know, it's just pure, incredibly precise engineering. So let's solve this mystery together.
Okay, here is our roadmap for today. First, we'll look at the global positioning segments. Then, controlling the constellation. Third, we'll tackle signal delays and errors. Fourth, we'll look into fixing the glitches. And finally, we'll wrap up with how all of this applies to oceanographic applications. Let's start right at the foundation with Section 1, the global positioning segments. So, GPS isn't just a bunch of satellites randomly floating around in space. It's actually a massive, highly coordinated three-part architectural system working in real time. Up top, you've got the space segment, broadcasting signals down. Then there's the control segment, with monitor stations scattered across the Earth, keeping a super watchful eye on those satellites. And finally, the user segment. That's the planes, the cargo ships, and yes, your smartphone, receiving that data to figure out exactly where they are. Now, to make this whole global net actually function, there is a magic number. 24. That is the baseline number of satellites in the GPS nominal constellation that you absolutely need to make true, unbroken global coverage possible. And they aren't just thrown up there. These 24 satellites are meticulously arranged across 6 orbital planes at a staggering altitude of 20,200 kilometers with a 55-degree inclination. The math behind this is just beautiful. This specific setup guarantees that a minimum of 4, and sometimes up to 12, satellites are visible in the sky from any single location on Earth at any given second. And since 4 is the absolute minimum you need for a 3D position fix, this net ensures you're always covered. Moving on to Section 2, controlling the constellation. Those satellites can't just be left alone up there. We have to talk about the unsung heroes on the ground, keeping this multi-billion-dollar network from drifting. Central to this whole operation is the concept of Ephemerides. Basically, these are the precisely calculated orbits of the satellites. You see, things like gravity and solar radiation are constantly nudging these satellites off course. So monitor stations around the globe collect data, beam it to the master control station, and then that station estimates the satellite orbits and corrects any atomic clock errors. And this isn't some annual maintenance check either. Ground antennas actually have to upload corrections to the satellites 3 times a day. That means every 8 hours, fresh orbit and clock data gets beamed up from Earth. Think about it. If they didn't do this, that helpful little blue dot on your phone would drift wildly out of place in just a matter of days.
Now, down in the user segment, there's a massive contrast depending on what you're actually trying to accomplish. A standard handheld hiking GPS that relies on the civilian's standard positioning service. It's great, but it's limited. On the flip side, professional tripod-mounted receivers are processing highly precise L4 position-fixing data. By utilizing L4 principles, these devices leverage advanced multi-frequency tracking and complex algorithms to achieve accuracy that your phone just literally cannot handle.
Which brings us to Section 3, signal delays and errors. Why do we even need those heavy-duty tripods and complex L4 corrections in the first place? Well, because the journey of a signal from space is pretty rough. As the signal travels 20,200 kilometers down to your device, it hits an atmospheric obstacle course. First up is the ionosphere, stretching from about 50 to 1,000 kilometers up. Up there, charged particles, ions, literally deflect and delay the radio signals. Then it plunges into the troposphere, the bottom 50 kilometers. Here, shifting humidity, temperature, and atmospheric pressure slow the signals down even more. And if the atmosphere wasn't bad enough, we have multipath errors. Honestly, this is where it gets kind of funny. You have this billion-dollar, perfectly synchronized space network, and it can be completely, utterly confused by a flagpole. Multipath happens when the GPS signal bounces off a highly reflective object, a car, a building wall, a flagpole, before it actually hits your antenna. Because the signal took a longer, bounced path, it arrives slightly delayed, totally throwing off the distance calculation. When you stack all these ranging errors up, a standard autonomous GPS can be off by a massive 7 meters. 7 meters. But check this out.
By introducing differential GPS, that error drops to maybe 2 meters. And when we apply RTK, real-time kinematic technology, we squash that error down to between 0.005 and 0.01 meters. We are talking literally millimeters.
All right, section 4, fixing the glitches. Let's look at how we actually get down to that millimeter level. We achieve that precision using some really ingenious terrestrial workarounds. The biggest leap comes from differential GPS, or DGPS. Here's how it works. We introduce a fixed reference station right on Earth. Since the station is physically bolted to the ground, it already knows its exact absolute coordinates. So when it receives satellite signals, it calculates the difference between where the GPS says it is and where it knows it is. It then broadcasts what we call pseudo-range corrections, basically mathematical tweaks to fix those atmospheric delays straight out to mobile stations like ships. To break that logic down step by step, step 1, the base station knows its exact physical location. Step 2, that base tracks the exact same satellites as the mobile receiver, which we often call a rover. Step 3, the base mathematically calculates the atmospheric errors happening in that specific local area in real time and sends those corrections directly to the rover. Boom! It effectively eliminates the atmospheric delays we talked about a minute ago. And this brings us to the absolute pinnacle. Real-time kinematic, or RTK. RTK takes that DGPS concept a step further. Instead of just looking at the data code, it tracks the actual carrier phase, the physical sine wave of the radio signal itself. This is what pushes our positional accuracy down to 2 centimeters or less. It is absolute mind-bending precision.
Finally, let's wrap up with Section 5, Oceanographic Applications.
You might be wondering, why do we even need millimeter-level accuracy in the real world? Well, let's connect all this heavy tech back down to the Earth's surface. Extreme spatial accuracy is literally the invisible backbone of modern marine science. When you're out on the open ocean, there are no landmarks, there are no road signs, no flagpoles to guide you. Without deeply corrected, highly accurate GPS data, studying the vast, featureless oceans would be nearly impossible. This tech directly enables hydrography, which is the measurement and description of the physical features of oceans, seas, and coastal areas. Its primary purpose? Navigation safety. If you're mapping a treacherous underwater reef to keep massive cargo ships from sinking, being plus or minus 7 meters off because of uncorrected GPS is a matter of life and death. You absolutely need that RTK, DGPS level exact position fixing to map those physical boundaries safely.
And this reliance spans every single branch of the science. Whether it's physical oceanography studying currents, chemical oceanography tracking salinity, meteorologists studying the weather, biological tracking marine life, or geological mapping the seafloor. Every single one of these disciplines depends entirely on knowing exactly where a measurement is taking place. Think about the physical tools scientists are tossing out there. They drop current meters to track water flow, Secchi discs to measure turbidity and water clarity, and reversing thermometers to capture temperatures deep, deep below the surface. A temperature reading from a deep ocean trench is completely useless to the scientific community if you don't have the precise, corrected GPS coordinates of exactly where you dropped that thermometer. The tech enables the science, period. So, we've traveled from satellites 20,200 kilometers in space, blasted through the ionosphere, dodged the flagpoles, pinged the base stations, and finally made it out to ships mapping the deep ocean. It leaves us with this final thought for today's explainer. If we can pinpoint a literal drop of water in a vast, featureless ocean down to the millimeter using signals from 20,200 kilometers in space, what are we going to measure next? Thank you so much for joining me to unpack this incredible invisible infrastructure, and I'll catch you on the next explainer.